Okay, so I already told in yesterday's class that there are three main topics for module 5. The first one is module 5 has three main topics. One is encoder, decoder models, encoder, decoder model, and then you have the prerequisite or non-popular object detection algorithm that I have not mentioned yesterday. Let me mention here. This is called RCNN. Before YOLO, this is the most popular, but after YOLO, YOLO was the most popular. And then the most popular YOLO object detection variants. So these are three main topics. Okay, other small topics are there, but these are the main things. Fine. So now let's start the first topic of interest, that is encoder decoder models. Okay, now let us see that. So here, even though the topic is new to you, already we have learned this in module 4 itself without explicitly mentioning this particular words, encoder and decoder. How? We will see with an example. So one of the RNN application that we have seen, one of the RNA application that we have seen is sentiment analysis. Now let us take a sample example. Some inputs I have. Movie is very bad. Now I will have this connections as part of my RNN. This is state S1, this is state S2, this is state S3, this is state S4. And I also will have the final result. Assume that instead of just mentioning it as positive sentiment or a negative sentiment, I would give the score. Maybe assume that it is plus, maybe it's maybe -4. Okay, -4 indicates that it's highly negative. Assume that my range of scores are -4 to +4, where -4 is an indication of high negative sentiment sentence, +4 indicates high positive sentiment sentence. Oh, before I forgot, Shiva, is my screen visible?
Yes, sir.
Great. Okay. So this is a way we have learned. Of course, here the score assignment was new to you, but generally in our previous discussions, we have seen the classification in the context of positive and negative. Now I'm just quantifying that positivity and negativity in terms of numbers, -4 to +4. In our case, in this particular example, movie is very bad. The sentiment score is -4, which is an indication of high negativity sentence. Perfect. Now I'm telling that in this architecture itself, we have encoder and decoder. You should be listening very, very carefully. When we highlight the encoder part here, this particular thing, people think that this entire thing is RNN. No, actually, this particular, the bottom part of your RNN is basically called as encoder. Actually, RNN is only the bottom part. What you do in the upper part of your network doesn't matter for RNN. So once you have S4, the job of RNN is done. What you do with S4, whether you get further extend the network or how do you print the output, it doesn't bother about that. So here it's -4. So this part is actually encoder. Now what is the encoder here? Encoder is nothing but RNN here. Then whatever the encoded representation that I have in the state S4 should be decoded so that I get the output -4. Now let me change the color again. The decoder responsibility is to take the state S4 representations and convert or quantify that into a score. Now this is basically a decoder. Now this decoder architecture is basically an artificial neural network, because this is my final state where I have just basic connections in the form of neurons. That's all. So basically, it's a ANN decoder. So that means the application that we have seen, the sentiment analysis application that we have seen, already has the concept of encoder and decoder, but I have not mentioned this while we're discussing this application. Okay, so it's very, very important, guys. I'll tell you one interesting aspect also. Yesterday, while we were discussing about bidirectional RNNs, while we were discussing about bidirectional RNNs, taking this as base, people have come up with very popular transformers like BERT. BERT, you know that it stands for bidirectional, bidirectional embedded representation transformers. Sorry, encoder, sorry, not embedded. Encoder representation transformers. So we have already discussed bidirectional, but I have not discussed about encoder. See, of course, this BERT, all these things are not part of our syllabus, as I said, as I mentioned here. But encoders and decoders will actually solve many applications, guys. Many applications. We'll see a few of them here. But you understood the main. Oh, Adit, you send now without listening to the class. Okay. So we'll see the possibility, Nana. I cannot promise you, but I'll look into the mail that you have written. If it's sensible, I'll check the possibilities. Okay. Okay. So encoder in this case is RNN, and the decoder is artificial neural network. Again, I'm emphasizing encoder and decoder is not a different concept. It is already there in the architectures that we do. And we're trying to project that in a new dimension in the context of this. That's all. Nothing more than that. Okay, this is one application. Okay. Now, let us take another application. So slowly I'm trying to build out the sensibilities behind the encoder and decoder modules. Now let us take one more example. Maybe the application 2 is predicting next word. Predicting next word. I think we have also seen this previously. Autofill the next word or autofill the sentence. So everything resembles the same. Fine. Now assume that I just want to do this. I've taken a sample sentence. You have a start of sentence, and I pass that start of sentence to my hidden layer. I have a hidden representation here, and I have an output. Assume that I, and I also have, I pass this output as input to this next state, where I just do connections as earlier. Am, again am would be the input for this next ANN and hidden representation, and assume that I'm just taking the output, I'm getting the output good, and good will be an input for this good, and again the hidden representation, and maybe I'm done with my sentence, and you'll have end of sentence or end of sequence. So this is the model for predicting the next word. It makes sense. Definitely it makes sense. But one thing you need to be very, very careful is where exactly the encoder and decoder lies. Where exactly the encoder and decoder lies. Obviously, the same logic applies here. If you take here, the bottom part of my architecture is encoder, and the upper part of my architecture is actually decoder. This application we have seen earlier, guys, but the terminology is only different. Okay, so encoder is again RNN here, and decoder is basically is traditional artificial neural network, because there are no connections in between the outputs. So it's basically a simple artificial neural network. But in this bottom case, we have connections. So definitely it's an RNN. Connections between the states. So it's an indication of RNN. Okay. So Now, if I ask, for example, assume that I stopped extending this further, and in the exam I asked a question like this. Write the equation. See, I'm just telling how the questions will come. Write the equation for the above architecture, precisely the decoder. Write the equation, write the decode equation, write the decode equation for the above architecture. What will be the decode equation for the above architecture? Can somebody tell me? Encoder is basically same. Traditionally, or either LSTM equations or GRE equations, whatever the same things we will discuss, it will come. It will be the same. But what about the decoder architecture? You need to write the equation in the context of application. For example, what is the probability of tth timestamp? Maybe this is my y1, this is y2, y3, and y4. Okay, that are my outputs. Whatever the output that I get, that would act as input to the next word. Okay, so there are certain caveats with this. I'll discuss slowly one by one. So what is the probability of probability of tth timestamp to get a word J given y1, y2, yt minus 1, given previous words. See, whenever I'm predicting good, I'm able to predict good not just because of am, it is also because of other inputs, I and other things. So when I want to predict the probability of a particular word at tth timestamp, I have to take the words that are outputted at different timestamps, that y1, y2, y3 till yt minus 1. Then actually this is the notation, but what is the formula for this? Is equal to nothing but softmax of V into ST plus C. V is the matrix, C is the bias. And what is ST? So since assume that it's Y2, then it is S2. Okay, so this is S2. So you take this S2 as input and you build out a probability distribution. And whatever the word that has having higher probability would be the next word that is to be predicted. Okay, as simple as that. The same thing we do for any traditional application using softmax and get the probability distribution. But the only thing is the terminology is different. That's the case. People generally tend to confuse. Sir, only terminology is different. So the concept remains the same. Yes, concept remains the same. Only terminology will differ in terms of encoder and decoder. That's all. That's all, and that's all. Okay. Now this is second application. Now, instead of before we go to some other applications in the context of encoder and decoder, what we do is we'll have simpler representations. We'll have simple equations instead of writing multiple times LSTM and GRUs and RNN equations. Let us try to put our understanding in a very concise manner so that I don't need to repeat the sentences or repeat the equations every time. For example, take the case of RNN. In the context of Rn, please remember these equations. In the context of Rn, at any state, ST equation is basically sigma of U into XT plus W into ST minus 1 plus P. I don't write this equation every time like this. Maybe can I write like this now? Rn of ST minus 1 XT. That means I'm telling that for the RNN, these are the two inputs, ST minus 1 and the current input XT. The hidden state from the previous timestamp and the current input timestamp XT. Okay, so these are two inputs. Why I'm not denoting U and W? Because those are the weights. Anyhow, they'll be trained. So once I have these inputs, the weights gets trained automatically. So this is the simplest representation that we will use from now. Okay, you can think the similar notations being used for LSTM and as well as for GRUs. Okay, for example, take the case of LSTM. LSTM equations, you remember, guys, it is ST tilde is equal to sigma of WHT minus 1 plus U into XT plus B. And you have ST that is equal to FT in terms of forward gate, ST minus 1 plus input gate IT and ST tilde. And you have HT that is equal to OT, and then you have sigma of ST. So this is basic equations, but I don't want to repeat these equations every time, unfortunately. So what I do is, if you observe clearly, I'll write either HT or ST. Both of them I'll just denote as LSTM of. What are the inputs for this ST? ST inputs are HT minus 1, ST minus 1, and what are the other inputs? XT. Okay, so I'm not writing like this one ST tilde, because ST tilde is also having inputs as HT minus 1 and XT. So I don't want to write ST tilde again. So yeah, let me just write this. Okay, so what are the inputs that I have? Other things are gates, and see if I'm not why I'm not writing other things. Either the other things that are left are weights and biases or the gates. Okay, so what are the inputs that I have? Highlighted things. H t minus 1, S t minus 1, X t. So this is simpler representation. Even though you said I don't understand this, there's no complexity involved in this. Just trying to put the inputs into one single notation, so other equations can be derived automatically. Okay, this is second. I hope you understood the logic behind this. So that it's only for my convenience, Nana, because I'm lazy. So I'm just writing this. Okay, I'm making myself simple in explanation. That's all. On a similar note, you can write the equations for GRU also. For example, if I don't know how many of you remember GRU equations. So you know ST tilde is equal to sigma of W OT and ST minus 1 plus U into XT plus B. ST is equal to IT gate, ST minus 1. All these things we have discussed. IT tilde. So IT tilde is not there. I think we can go for IT gate only. IT. So ST tilde. So again in this, what are the inputs that I have? The inputs are ST minus 1 and the input is XT. Rest of them are either weights or gates. So finally ST is equal to GRU of ST minus 1 XT. Okay, this is just a note, Nana. Before we proceed, the next important application. See, before we proceed the next important application, I just want to simplify the notations. The most important and the major application that was favorite for me is image captioning. Image captioning. Now, till now, if you observe, I have discussed the sentiment analysis and I've shown that encoder and decoder was hidden in the sentiment analysis architecture. Even in the next word prediction also, the encoder and decoder was hidden. Even the same application, same analogy can be applied even for POS, parts of speech tagging also. The encoder and decoder lies in the architecture itself. These are already known applications for us in module 4. Now we are in module 5. The new application that I can explain in the context of encoder and decoder is image captioning. This was not discussed. This was not discussed, Nana, because I already told yesterday, why do we require encoder and decoder? Basically, till now we have learned CNN, RNN, and DNN. Now, whatever the architectures that I have told, parts of speech tagging, sentiment analysis, all those things combined RNN with DNN or RNN with ANN. Okay, DNN or ANN. Now, can I combine, instead of, till now we have seen RNN with ANN only, but can I combine CNN plus RNN? Yes. So the image captioning is one of the application where it requires a combination of two architectures, that is CNN plus RNN. Very, very important combination, very, very crucial application. But how do we connect? That's most important thing. How do I connect CNN plus RNN? Guys, one important analogy that I want to give at this point is, many of you have completed your electronics course where you do certain circuit connections on the breadboard. So there are various connections. If I take two wires, I can connect serially or I can connect parallelly, right? Similarly, CNN is an architecture RNN is another architecture. I can connect both these architectures in different possible ways, and we will see all those ways. If you're comfortable with all these possible ways, you're good to go for solving even complex applications, because more majority of the complex applications will use more than one architecture. Okay, so this is very important for your resume building if you use this state-of-the-art modules. Okay, let's come back to this. And I'll show you how to actually combine this both guys. Now, firstly, what I do is I have a CNN. Firstly, what is image caption? See, think that you have been asked to generate a caption, for the image. Generate a caption for the image. Now you need to really think. If I have some image where I have some person, I'm very bad at drawing. Just think that there's a person and there is some football. Okay. Now assume that this guy is playing with this football. This is an input image. Now, what is the caption that I'm expecting? A man is playing with football. So this is the minimum caption that I expect automatically to be generated by the system. That's perfectly fine. See, this is perfectly fine for the novice user, but as a deep learning engineers, we should really think how to model this application. Can anybody give some idea how to get this answer? So definitely, what is your input? Input is image. What is the output? Text. Now, should I use CNN first, or should I use RNN first, or how do I connect both? How do I model this? How do I make my system understand and get the required output as the caption? Any guesses how the model will look like? Any guesses?
So taking pixels first and then doing convolution operation, after that flattening it.
Great, great. It's perfect answer. Great, Shiva. So whatever your friend told is almost right. So let us try to decode his answer. Firstly, my input is the image. You already know that CNNs are very, very popular for the image data sets. Okay. Now what I do is I pass this input. Maybe I'll just copy the, okay. Instead, I could have drawn it. Very simple diagram. Okay, fine. Okay. So this is my input. Don't blame me by just drawing a particular diagram in the worst case possible. I think I'm the only one who draws it this worst case, or in the worst way, but this is only for the demonstration. Okay, fine. So this is the image, input image. What I do is I pass this to any CNN. It can be VGG, it can be ResNet, it can be any of your standard architectures, or it can be your own architecture if you're confident about the robustness of it. Then what I do is the output of CNN at fully convoluted layers, whatever the fully connected layers, what are the output that I get? Whatever the output that I get, I will pass to the RNN. See, whenever you have CNN, you have certain convolution layers, max pooling layers, convolution layers, max pooling layers like this, and then you have fully connected FC1, FC2, and FC3. Assume that after FC3, assume that FC3 gives the probability distribution. The output of FC3 is probability distribution, says that it's a person or it's a ball or something like that. But I don't want the objects to be detected. I don't want something else. So I don't bother about the last layer of my CNN. I don't want the predictions. I don't want the softmax distribution. Instead, I want the fully connected layers, and I need to flatten the entire output and pass that as S naught to my RNN, because RNN have states S1, S2, S3. I already told long back S naught is by default 0. Later we will see Later we will see either the programmer can initiate this S0 or it can be taken from some other architecture. So now whatever the output that I get from fully connected layers, that is denoted as S0 for my RNN. Where is RNN here? Let us see that. So this is my S0. I'll just pass it like this. And here I would just go like this. I have an RNN architecture like this. Oh, maybe I'll just draw. I'll just draw like this. Okay. I have it in representation. I have an output, and again hidden represent input, hidden representation output, input hidden representation output, input hidden representation output. Like this, it goes on. Okay, so I don't want to do all the connections. It is take time consuming. Oh, sorry. Okay. Now, here I expect my RNN to generate the sentence in a more appropriate way. So what is the sentence that I'm expecting here? A man is playing with football. Okay. So what it does, it will start with start of sentence, and it takes a man, that A will be given here, a man, that man is given here, is given here, playing, like that, playing will be given here. Okay, then we'll get with, then with will be given here, and football. Okay, so man is playing with football is the expected answer like this. Now, I cannot generate this sentence directly from the sky or somewhere else. What should be the input always? Whenever I want to generate this sentence, I require the abstract understanding or the feature extraction from the CNN. So this is, you know, that this particular thing is state S1, this is S2, this is S3, this is S4, it goes on, and this is S0. What is S0 here? The same S0 here. I'm just giving the feature extraction that was done from fully connected layers, so the abstract representation from the fully connected layers as state S0. Okay, so definitely what is happening here, to generate state S1, S0 will influence. Even to generate S2, to get state S2, S1 influence, and as well as S0 also will influence. To get state S3, S2 will influence, and as well as S1 also will influence. Similarly, to get state Sn, all Sn minus 1 states will influence to get the state Sn. Okay, so definitely the influence of S0 will exist in all my states. Okay, but can you just tell me the disadvantage of this? See, I'm connecting CNN. See, if you observe clearly, guys, this particular architecture, whatever you see, this is RNN, and the particular architecture that you see here, this is CNN. I connected CNN output to the RNN like this. Like this, I connected CNN plus RNN. Perfect. But this is one possible connection. But there is certain disadvantage with this connection. Can you tell me the disadvantage? Think, Nana, think as a designer, think that you are really facing this problem, and think that you only have to solve this problem. No other one is there to solve this. Now tell me this. What is the problem with this connection? Think, really think.
So kernels will be more.
Okay, kernels will be more. Okay, perfect. Which kernels you mean to say? CNN kernels?
Yes, sir. After flattening, we'll get so many inputs, no, sir.
Okay, that's fine. Okay, but see, the abstract representation, whatever we have for the image that cannot be changed. See, at any point, instead of printing the objects in the image, I'm just removing the last layer, and whatever the output that I get, the abstract representation from non-last layer, I'm just taking that and giving that understanding to my RNN so that RNN generates sentences. So I really don't think that the number of kernels would make a big issue, because it's standard across the configuration that you take, irrespective of the application. The same standard architecture you have to use. Actually, I'll tell you the problem is. But I appreciate you have tried your best. That's a good thing, good thought process. Now, here, if you see very carefully, I connected CNN only once. Think that the SN that you have is very large. Assume that I have a very big sentence to be generated. Assume that I want to generate a sentence with 20 words. That means I'll have 20 states, that is S20. If whenever I'm getting the S20, the input S0, that is nothing but the CNN understanding, cannot influence much on S20. Maybe on S1, the influence of S0 is very high, but on S20, the influence of S0 is very, very small, very negligible. But assume that, not assume, actually, that should not be the case, because every word that I generate is part of the image. Based on the image objects only, based on the actions in the image, I'm generating the sentence. If I forgot what is there in the image, if I forgot by the time that I reach S20, I forgot what exactly S0 has. If I forget, there is no point in generating appropriate sentences. Then by this time you reach here, you, instead of saying a man is playing with football, a man is playing with some car, because this guy is S0 keeps on transforming, and by the time it reaches SN, system could not understand any abstract representation from given from CNN, so which is very bad. Now, how do we solve this problem? I think you can come up with the solution. Any solution now? Any solution, guys? What shall we do? You already, I'll give you the hint. We have done this in our one of CNN architectures, Microsoft architecture, Microsoft CNN architecture. This is a very common thing. Whenever you have more transformations or more morphings, what do you have to do? Any answers? Okay, others I'll tell you. No problem. See, I think you're hesitating to tell, but I think many of you have got the answer. Instead of connecting the S0 only to this part, what I do is I just connect the S0. I just connect the S0 to every state. That means I connect S0 here, I connect S0 here, I connect S0 here, I connect S0 here. That means along with the inputs, I connect my S0 here. Here I'll connect the same S0, I'll connect here, the same S0 I'll connect here, the same S0 I'll also connect to all other states. What happens with this? If I connect like this, even to generate a particular word in the last state, this particular state SN will know the complete abstract representation of the image. The transformations will be very, very less. Only the direct representation that system understood in terms of CNN, whatever the system and whatever the understanding that my system has with CNN, that understanding is directly given to RNN, so it can generate an appropriate word at that particular state. Okay, so this is a theme that we can think of to address the previous problem. Okay, now in this case, what about the equations? Now, okay, why I'm discussing all this? What is encoder here? What is encoder here? Where is encoder here? Encoder is basically this one. This entire thing is encoder. This entire thing is encoder. The CNN architecture is encoder. Encoder in our case is CNN. And what about the decoder? Decoder would be this one. This entire thing would be the decoder. In our case, what is decoder? Decoder in our case is RNN. Sorry, I forgot to tell you. I was mistaken here. This entire thing is decoder, but decoder has two things: RNN plus ANN. Because I want to erase this. The decoder has two parts. The bottom part is RNN, and it also has the upper part where I have ANN. So decoder is a combination of RNN plus ANN, and encoder is actually CNN. Okay, so this particular application is very, very important for you guys, so that you'll understand how to combine the CNN and as well as RNN plus ANN. Okay, now this is the architecture point of view, but how do I frame the equations? That's important, right? That's the reason I've taken the simpler representations. So it's actually ST at any timestamp. We have ST at any state T. We have the RNN. RNN always takes the previous state, that is ST minus 1, and it also takes the current input XT. This is the traditional RNN architecture that we have seen earlier. If you see earlier equations that I've written here, see this is the equation. If you see, it's ST minus 1 XT. Now, in our case, we need to extend this equation along with ST minus 1 XT. What exactly system will receive, Nano? What exactly system will receive now? In this case, in the image capturing case, the RNN not only receives the previous state, not only receives the current input, it also receives something else. What is that? It is basically the abstract representation from my CNN. Okay, so that is maybe assume that fully connected layers representation. What are the fully connected layers representation I have in the image, that will be passed. Okay, so whatever the abstract representation that I have in terms of CNN architecture, by taking image as input and the output of fully connected layers is also given as input to my RNN to finally get the state ST. Based on the state ST, I would predict the word at that timestamp, and I call that as YT cap. Okay, this is a very, very important aspect that you have to really remember. Okay, so in this case, if I just want to further denote this in the matrix form, it's actually, for example, take the case of S3. If I want to get S3, so here we have taken a simpler notation where I don't have weights. But if I want to write the same equation in terms of weights, it will be some sigma W into S2, the previous state, plus some U into X3 comma S naught plus B. Now you realize the same equation that I have written above, I'm just writing that again, but now I'm just trying to represent in terms of weights. Now, first thing is ST minus 1. Here it is ST is 3. So ST minus 1 will be 2. And I have some matrix W. But now if you see, I have two more inputs. That two more inputs is nothing but XT. X3. T is 3 here. So X3. And what is FC of I? FC of I is denoted as S0. That is 0. I'm just keeping this. And I'm trying to use a single matrix U. Why? Because I already told, if you observe this, for every timestamp, I have inputs, both. I have input, the S0 and as well as the current input. S0 current input, S0 current input. Okay, so S0 and the current input. See, and here X3 can be of one dimension, S0 can be of any other dimension, because S0 is actually an abstract representation. It can be of any size. That depends on the CNN architecture that you use. So what people do is, when you have different sized matrix representations or vector notations, so what they do is, they just take the x3 in the vector form. They take x3 in the vector form and they take s0 in the vector form, and they just add both the guys. They just add both the guys irrespective of the size. Okay, rest of things will be converted into sparse representations and then they'll be added. And whatever the final representation that was there after adding, that would be multiplied with u and add the bias to finally get the state S3. Okay, do not get confused. It's basically very, very simple like above equation. But here, why you have to combine x3, why have to combine x3 and as well as S0 with single matrix U? Because along with the current input, the state is also being passed. The S0 state is also being passed as input. Okay, that's the reason I've used U common matrix for both x3 and as well as S0. Okay, so I hope it is very clear to you guys. If you don't understand this, I think you understood, but yeah, otherwise you can ask me also. If you don't understand this, at least you should be very comfortable with this particular equation. So it's same thing, S3 minus 1 xt. Along with that, we're also passing the image output, which was there as an abstract representation of CNN. Okay, that's all done. But if I want to simplify this, if I want to write everything in one slide, let us see that. Now, what is input here? Input is image. Next one is encoder. What is encoder here in our case? Encoder would be some S0. That is a state, input state for my RNN. So it's actually CNN, some CNN, any CNN that you use. And the image that you have, assume that this image is denoted as some maybe xi. Image is indicated by xi. Then you pass xi image to CNN and to get the abstract representation in terms of CNN. So that is my S0. And what about decoder? What about decoder? Decoder is basically ST, RNN, some RNN. I already have written this ST, but I'm writing in a single set, ST minus 1. And I also have XT, fully connected representation of the image XI. Okay, so, and then you have this. And once I have the states, I already told this encoder is CNN and decoder is RNN, but the other decoder, the other architecture in the decoder is ANN. Okay, that's basically simple artificial neural network. So what I have to do is I have to get the softmax. I have to get the softmax of ST, whatever the final state that I need to get the softmax, multiply with the weight matrix V and add the bias. So this is basically what the probability of a particular word yt given all previous words y1, y2, y3 till yt minus 1 along with image. That means I get the previous outputs and also the abstract representation of the image. So I think it makes sense not to write I here. I should write S0. So I got all the previous outputs in my RNN. I also got the abstract representation of my image to predict the current.
It should be XI, no, sir. Not as S0. It should be XI.
No, XI is image.
Yes, sir.
XI is image. I should not pass the XI to my representation directly, right? I should pass S0 always to this ST. What is the input? If you observe here, the input is S0. I'm not passing image directly to this. I'm passing the abstract representation. That abstract representation combined with input and apply softmax to get the current output. Okay, Nana? Clear?
Yes, sir.
Yeah. So that S0 I'm passing, and finally taking the S0 and taking the previous outputs what is the probability of the current word. Here it's very, very important, guys. I don't know whether you are clear with this or not. Here, whenever I am generating a caption at a particular timestamp, for example, I'm just giving some caption here, some abstract representation, some output. Assume that I am getting playing. My system treated as playing. See, do remember, guys, you should not forget the basics. I will not get the word as output directly. What will I get? I will get the softmax distribution. Now, what is the length of this softmax distribution? Can you tell me, guys? What is the length of the softmax distribution? How many entries will be there in this softmax distribution? Anybody? I'll really appreciate it. It is nothing but number of vocabulary words. If the number of vocabulary words in your corpus is 2000, then for the entire 2000 words, you'll get the probability distribution. And at a particular state, you will have the highest probability. At some point in your entire matrix, you will find the highest probability. Assume that the highest probability is 0.3, and this 0.3 is associated with the word playing. That's the reason I have predicted as playing. You should not forget the basics. Okay, so what if this is very, very important, guys. What if my true word is playing? I expect at this particular timestamp t, I expect the word to be generated as playing, but assume that your highest probability 0.3 you got not for playing, it's for running. Assume that. Then you have a loss. You expected your true distribution is your true word that you are expecting is playing, but your probability distribution is giving highest probability for the word running. Then definitely there's a loss, right? There is a loss. Now we need to overcome this loss. Yes or no? We need to reduce the loss. How do we reduce the loss? All that things we will see later. Okay, whenever you have a loss, how to reduce this loss? We'll see that. So the next thing is loss. You understood what is loss here? Where exactly the loss will come? Of course, whenever I expect some word to be predicted, but the prediction is not that word, definitely loss will be there. But how do we overcome this loss and how do we adjust this loss? All those things we'll see that in the next class. I think next class will be on next week because I think you don't have class on Thursdays and Fridays, I suppose. Fine, whenever it may be the next class, we'll try to see that. Okay, that's all for the day, guys. Let me stop the recording and take your questions.